Hello everyone. This is the third part of lecture one. Okay, so in the last portion of the second part, I told you that there are six basic component parts of a typical fermentation process, which are like formulation of the media, then sterilization of the media, fermenters, and all the associated ancillary equipment, and we have to produce a active pure culture in sufficient amount, and we also have to set all the optimum conditions for the optimum growth and production. Okay, and then we have to extract the product and purify them, and finally proper disposal of the effluent. So these six are the major component parts of a typical fermentation process. Okay, anyway, so all these component parts basically you can categorize them into two group or two steps. One is upstream processing and another is downstream processing. Okay, the upstream processing, there are main there are three main areas. One is the producer microorganism, fermentation media, and fermentation process. So among these, in case of producer microorganism, in this step, it actually also include several other processes. Okay, so the processes are like first, what we have to do first, we have to obtain a suitable microorganism. Okay, then we need to improve this microorganism. That means first have to isolate a good strain of the microorganisms. Then we have to study with it. Okay, we have to improve it in a way which will increase its productivity and yield. Okay, so well, let's keep one thing in mind here. Improvement does not mean that we will do everything genetically. Okay, so in most of the cases, actually, the thing is like that: we first isolate a microorganism, okay, a strain of a microorganism, and we try to provide them optimum nutrients and nutrient requirements. Okay, we try different types of carbon source, energy source. We provide them different pH conditions. Okay, and then we try to find out which conditions are the most optimum for that particular strain of the microorganisms. Okay, which will, where they will give the maximum product. Okay, and sometimes we can also use genetical processes, genetical methods to improve our strain. Okay, sometimes we actually do that. However, then after you got your strain, you improved it, then it's very important that you have to maintain it. Okay, maintain the purity of that strain. So this is actually very important, right? So you got a very good strain, so if you cannot maintain it in a pure form, it will be a disaster. So you have to properly store it and maintain it with purity. Okay, and then you have to prepare a sufficient amount of your strain to put it in the final fermenter. Sometimes it is also called seed culture. Okay, so you have to prepare the seed culture. Okay, this figure, okay, this photo shows all the, it's kind of a summary photo which shows all the steps or procedures which are part of the upstream processes. Okay, uh, so if you first think about the microorganisms, we actually already talked about it in this slide. Okay, so what we have to do, we have to isolate our strain. Okay, and then we have to do the improvement, and after improvement we will get our strain. Okay, so sometimes, after improvement, you get the strain and you try for the fermentation in a small scale, in laboratory scale fermenter, and you see that, okay, the yield is not that good. Okay, you expected more. So in that case, actually you can again do some strain improvement. Okay, and after doing it, finally you will get your strain which will use for the fermentation. Okay, this is and this strain is called production strain. Okay, and in during this process, I mean, when you will do the strain improvement and make your production strain, actually, you have to try everything, right? So you have to check the nutritional requirements, the metabolic controls, the sensitivity of your strain. Sensitivity is important because in the final fermenter we do some stirring. Okay, so whenever you are doing stirring mechanically, it creates some forces which is called shear force. So you have to check whether your final production strain is stable, can withstand that shear sensitivity. Okay, and you have to check the temperature, optimum temperature, oxygen, carbon dioxide requirements, everything. Okay, you have to check the genetic stability, the metabolic byproducts of your strain, and you also have to check the viscosity effects. Okay, because in the final fermenter there will be certain viscosity. So you also have to actually check that what kind of effects that viscosity can affect in the production capability of your strain. Okay, okay, so after doing everything, when you get your production strain and you got all the optimum conditions and requirements, then you will have to prepare the starter culture, that is the seed culture, which we will put into the final big fermenter. Okay, so this is about the microorganisms. You also have to do many things with the media. Okay, the culture media. Okay, for the fermentation. So in case of media development, we you have to start with the raw materials. So you need to decide, I mean, which raw materials you are going to use as a nutrient source, like source of carbon, nitrogen, phosphorus, sulfur, minerals, trace elements, growth factors, etc., right? So now, when I mean, in case of industry, I mean, we use a very, a big fermenter. So that means you actually need lots of raw materials there. So if you think about the industry, you always have to think about those raw materials which are like more cheaper. Okay, so in that case, actually, you have to, I mean, when you will think about the raw materials for your industry level fermenter, you have to consider several things such as availability, how easily you can get those raw materials, what is the cost, how stable your raw materials, okay, what kind of pre-treatment and sterilization is requirements. Okay, because these are important. I mean, if the source is not available, okay, if the pre-treatment and sterilization requirements is tremendous, the cost will be very high. So if the cost is very high, it will not be feasible or suitable for the industry. Okay, so anyway, so you prepare your media. I mean, you developed your media. Then after you developed your media, then usually we use the same media for the final fermenter, and also during when we produce the or make the starter culture, the seed culture. Okay, so that means we use this same media as propagation media and also as the production media. Okay, in case of maintenance media, sometimes we use the same media, or sometimes we need to do some modification to use it as a maintenance media. Okay, basically it's depend on the strain of your microorganisms. Okay, okay, so you prepared your starter culture, you prepared your production media. Now you put them everything in the fermenter. Okay, so you prepare your starter culture and you prepare your production media. Will you just put them in the fermenter? No. Before doing that, actually you have to prepare your fermenter. Okay, you have to clean the fermenter properly. You have to sterile it. Then you will put the starter culture and the sterile production media into it, and you will do your fermenting. You will do your fermentation. Okay, so now basically, I mean, in the fermentation, in the final fermenter, you again have to provide everything optimally. So what you have to provide, like, I mean, for the fermentation, you have to supply oxygen. So how you will do the aeration to provide oxygen? Okay, so you need to do some stirring. So what kind of steering mechanism you will use? What will be the design of your fermenter? What will be the size of your fermenter? What will be your mode of operation? Okay, I'll talk about the mode of operation later. So what will be your mode of uh, operation? Okay, so you have to decide everything beforehand. Okay, okay. So basically, you have to find out the optimum of these things, like what design will be optimum, okay, most efficient, what kind of steering mechanism will provide, I mean, will allow us to get maximum product, okay, what will be your aeration speed and mechanism, okay. Also you have to put various controlling device there to control the pH, to control the pressure, control the foam, cooling and heating system, okay. Basically you have to decide everything before you go for the final reactor, okay. So when actually we do this, in case of, I mean, industrial microbiology thing, okay, so these are not everything, the steps I mean shown here, these are not everything actually. What, I mean, like, so, okay, think this way. You are a scientist and you want to develop a fermentation process, okay, to produce something. So first step, you isolate your strain and you did all your improvement process, and finally you got your desired production strain, okay. So these steps, I mean, until you get your desired production strain, basically these are done in a small scale. So usually people do this in the laboratory using a small scale fermenter like 5 liter, 10 liter, or maybe people can use even 50-liter fermenter. Okay, so we will do everything in a small scale. So then after you got your desired production stream, you will not directly go to the big fermenter. Okay, you will not directly go for the starter culture propagation. Actually, after you're done in the laboratory, you have to scale it up step by step, okay. So like in the laboratory maybe you use 10-liter fermenter, so then you will use maybe 5,000-liter fermenter, okay, or you may will use 10,000-liter fermenter. These are called piloting, okay. So these are called pilot fermenter, okay. So you, I mean, what's the goal of using pilot fermenter? To scale up the process, I mean the process that you have developed in the laboratory. Before going to the very big final fermenter, you need to scale it up, okay. So for a scale up, we usually use like I mean 5,000 liter to like 25,000 liter or 20,000 liter okay. So this size fermenter, okay. So actually during your piloting, so I mean when you are scaling up your fermentation process, you are using the pilot fermenter. At that time you have to fix all these things. I mean what kind of agitation, aeration you will use. Okay, you have to actually I mean what design of the fermenter you will use. You have to fix all these things there. Okay. So anyway, so these are the, I mean, all the processes of the upstream processing. Okay, now the downstream processing. Okay, the downstream processing start after the fermentation is done. Okay, so upstream processing involves all the processes till the fermentation. Okay, so your fermentation is done, okay, shut it down. Now you will start the downstream processing, okay. And the downstream processes that follows fermentation are these: cell harvesting, cell disruption, product purification from cell extracts or the growth medium, and waste disposal. And this slide, it's a kind of a summary slide of the downstream processing, okay. So what's the first step of downstream processing? I mean, your fermentation is done, so now you have to harvest your product, okay. So the first step is cell harvesting. So in which method you will harvest your cell, I mean in which method you will harvest your product depend what your product is. So for example, your product is extracellular, that means the organism, microorganism that you are using will produce the product and will secrete it. That means your product, here your product is in the liquid portion, not in within the cell. So if your product is extracellular product, you have to harvest the liquid media, okay, not the cell. But if your product is a intracellular or periplasmic product, so in that case you have to harvest the cells because your product is in the cells, okay. So now this harvesting you can do by like cell separation. I mean, you have to separate your cell from the media, so you can do by centrifugation or filtration. But centrifugation is not a very efficient method if the volume is very high. Say you did fermentation 1 lakh liters. 1 lakh liters is huge, right? I mean, centrifuging 1 lakh liter is actually tremendous. It's tough. Okay? The cost will be very high. So in that case, I mean, when you have to deal with large volume of media, uh, filtration is a better way, more feasible, more cost effective way. Okay. Okay. Anyway, so you harvested your media, and I mean, if your product is extracellular, it's in the media. So then you have to concentrate it. This is important because now you have 1 lakh liter of products. Okay, it's very tough to deal with this big amount. So you need to concentrate them. Okay, and in case if your product is intracellular or periplasmic, you have to harvest the cells. Okay, then you have to disrupt the cells because your product is inside the cell, so you need to break it down. So you will disrupt the cells, okay, and then you will harvest. You take the portion which portion contains your product. Okay. Okay, so you harvested your products. So now you need to purify them. So how you can purify them? You can use different methods. And which differ on what kind of different methods? You can use dialysis, precipitation, partition, chromatographic steps, ultrafiltration, distillation, etc., etc. So which method you are going to use is depend on your product. Okay, so what type of products what type of products you are going to purify. Okay, depending on that, you have to choose what kind of purification method you will use. Okay, so you have you did the purification, then finally you have to make your finished product. Okay, so it actually also done in different way. I mean, it's also done in different way based on your products. You can do crystallization, you can just dry it, you can lyophilize it. Okay, you can do some sterile filtration, and then you will package your product. So you are done with your finished product. You got your finished product. Okay, so these are the downstream processing. However, there is another important part of the downstream processing. It's effluent treatment. So if you look at this figure, in different step, you will get some waste product, like, right. Suppose, for example, in this case, so you collected your media, okay. So you got the biomass, the cells, the biomass as a waste, okay. So or you get your your product is in the cell, so you harvested the cell. The spent media itself is a waste, okay. And where you disrupted the cell, you get cell debris, okay. And during purification you get some more waste products, okay. So every step you'll get some waste products, and you just cannot throw this waste product in the environment, okay, because this waste product contain mm, various dangerous things. They can contain the harmful, I mean, they can contain microorganisms which maybe can be, I mean, dangerous for the environment. Your waste product will contain lots of harmful chemicals which are, which are harmful for the environment. So before disposing your effluent in the environment, you need to treat them properly. Okay, you need to make them safe for the environment, then you can dispose your waste. This is called effluent treatment, ETP, effluent treatment plant. Okay, in old days, ETP was not a thing which people used to consider. I mean, most of our industries they used to didn't think about the ETP, the effluent treatment, because if you want to establish a ETP plant, it will increase your cost. So it's it's always benefit. I mean, it will be always good for the industrialist if they just can avoid the effluent treatment. But it will be dangerous for the environment. And nowadays the regulatory authorities they got strict, so they require that. You should have a effluent treatment plant. Also, like the industry who export, okay, the importing countries, they are some nowadays very serious about the effluent. Okay, so nowadays actually our industries they are establishing the effluent treatment plants because those are regulatory requirement or required to export your items or goods. Okay, so anyway, so we are done with the upstream and downstream processing. Okay, so now I will talk about the types of fermentation techniques. I think I already talked about this in some earlier slides. But anyway, just for the recap, so the fermentation techniques we can divide it into basically two groups. One is surface fermentation, another is submersion fermentation, or you can say surface techniques or submersion techniques. Okay, and the in case of surface techniques or the immersion techniques, we we grow our microorganisms or organisms on the surface, solid surface. And in case of submersion techniques, we grow our organisms in the liquid. Okay, and the submersion techniques, we can run the submersion techniques in three different ways: batch, feed batch, and continuous process. Okay, so I'll talk in about this in more details in later slides. So first, the surface or solid substrate fermentation. I already said this one. Right? In this case, we grow our microorganisms on solid surface. Okay, and in this case, usually the substrate itself acts as carbon or energy source. Okay, and in absence or near absence of free water. However, those cannot be completely dry. Okay, if it's completely dry, your microorganisms will not grow. Okay, so there will be very limited amount of water, but moist will be there. Okay, this slide shows some example of solid surface. Example of substrates which provide solid surface for the surface or solid surface fermentation. Okay, such as I'll just name one or two like the rice straw, corn. Okay, wheat straw, like the logs, wood logs. So those surfaces are solid surface. The peppers, okay, the surface is solid. Okay, so these are some example of solid surface which are used for solid fermentation. Okay, okay. So basically, these itself are the substrate. When these are used as surface, these are used for surface fermentation. These itself are the substrate. Okay, okay. This table it shows some example of the use of solid surface fermentation. Okay, some application of the solid surface fermentation. Please see this by yourself. I'll just I'll just read one or two. Like for example, in agro or food industry, example traditional food fermentations. Okay, such as fermented cheese, tempeh, cozy. Okay, okay. These kind of foods are not so famous in our country, but in many countries, people like these things. Like they like fermented cheese, especially in the European countries, I guess. Okay, in Japan, they also like some fermented food. You know the tofu. Tofu is made from soybean. Japanese people love fermented tofu. Okay, so it's also fermented tofus are also produced by fermentation. And in that case, this SSF, that is solid state fermentation process, is used. Okay, also SSF has application in the agricultural field. Okay, for example in biocontrol or bioinsecticide. Okay, It has SSF also has application in the industrial fermentation, in enzyme production, antibiotic production, organic acid production, etc. Okay. Okay, so now this slide, it shows side by side comparison between the solid state and submerged fermentation process in regards of these characteristics. Okay, so you actually already know about this one. Like in case, I mean, if you consider the microorganism in solid state, they are in a static condition, they don't move. But in case of submerged fermentation, they are in continuous movement because we agitate them, we stir them. Okay, and water uses limited in solid state, submerged state unlimited. Submerged state needs lots of water. It's, I mean, we do submerged fermentation in liquid form. Okay, and in case of physical energy requirement for solid state, physical energy requirement is low. Okay, but in case of submerged, energy requirement is high because in submerged fermentation you need to stir it mechanically, so it will require more energy, right? But in submerged, the human energy requirement is low because usually we do submerged fermentation in a fermenter. Everything is done kind of in automated or semi-automated way. So humans are not necessary there. But in case of solid state fermentation, you will need many human. Okay. And capital investment for solid state is low, for submerged is high because you have to use the machinery. Some machineries are costly. So this slide, it talk about some economical and industrially important advantages of SSF. I mean, these are some advantages of SSF. So what are those? Lower capital and recurring expenditure, lower wastewater output because very few, I mean, less amount of water is required here, so wastewater will be also low, right? Energy requirement is low, simple procedure. Fermentation made is simpler, like you just can use the straw, rice straw. Okay. uh, we don't need rigorous control of fermentation parameters. Okay, usually in the submerged fermentation you have to very strictly, very rigorously control all the parameters. Okay, aeration is easier, economical to use even in smaller scales. Applicability of using fermented solids directly. I mean, after the fermentation, you can use those fermented solids directly. Okay, storage of dried fermented matter, lower cost of downstream processing. Downstream processing is very cheaper here because usually we directly use the fermented product. So okay, so that kind of harvesting, that kind of harvesting and purification is not necessary here. So that's why downstream cost of downstream processing is actually very low in this case. Okay. So if you want to do SSF, you need to uh, consider some factors like which strain you will use, the design of medium for fermenter, the condition of the substrate. I mean, in this case, the substrate itself is this act as a source of the carbon or nitrogen, etc. Okay, so you need to decide. I mean, in which condition your substrate will be. So do you need to just use them in a dry condition, or you need to put some water there, make them wet before you use them as a substrate. Okay, so how you will control your fermentation process, what will be the design of your reactors. Okay, so you have to consider all these factors if you want to do SSF. Okay, we are done with the SSF, solid state fermenter. Now let's talk about the submersion techniques. So you already know, in this case we grow our microorganisms in the liquid culture, okay, the liquid condition, and we can do this by three different way. Okay, these are called different types of submerged fermentation techniques. Okay, one is batch fermentation, continuous fermentation, and then fed batch fermentation. So first, batch fermentation. So what is actually batch fermentation? I mean, in this case, we do batch by batch. So what do we mean by what we mean by batch here. So, like say you want to, I mean, you will do fermentation by batch system. So, you will put everything. You will put the microorganisms and the your media, liquid media, that's the substrate, into the fermenter, and you just turn it on. Okay. So and the fermentation processing will goes on until you turn it off, or you can say not until you turn it off. I mean the fermentation process will goes on until it stops. Okay, so actually what happened here? I mean you just put your microorganisms and the liquid media or the substrate there. Okay, and you just turn it on. So the microorganisms will keep growing. They will use the substrate, okay, and will produce the products, which can be a metabolites. So as time will go, your the substrate, that is the media, will get depleted. Okay, the amount of the substrate will go down, and on the other hand, the products, the metabolites, will accumulate, and along with the metabolites, some toxin will also accumulate, right? Whenever organisms grow, they produce toxin, right? So the nutrition will get depleted, and metabolites and toxic products will be accumulated in the fermenter. So the growth of the microorganisms will cease. Eventually, it will completely stop. I mean, the growth of the your microorganisms will completely ceased. So at that time, actually, you have to actually stop your fermentation. Okay, it's actually done. I mean, it doesn't matter if you want to keep it, if you want to continue it, it will not continue. Yeah? So it's already done. I mean, your microorganisms are already kind of dead. So okay, so once it's done, so then now you have to harvest your product. Okay, you have to harvest your product, you have to purify them, and you have to I mean you have to make your final product. Okay, that's it. Okay, so okay, I mean that's not all actually. So you harvested your product, so then what you will do, then you have to take out all the residual things from your fermenter. You have to clean it, I mean vigorously. I mean you have to clean it very well. Then you have to sterile it so that you can use it for another batch. So batch. Okay, so that's why it's actually batch fermentation. You do one batch of fermentation, then you do another batch of fermentation, then you do another batch of fermentation. Okay, so if you graphically want to represent the incidence of batch fermentation, we can show it in this way. So in x-axis, if you put the time, in y-axis if you put the concentration. So as the fermentation will go on, the concentration of substrate will go down, and that is the concentration of the substrate will get reduced, and the concentration of cells will increase. Okay, until their growth ceased. Okay, so now continuous fermentation. So in case of continuous fermentation, by the name we know, like this process will keep continuing. So how we can achieve this one? So in case of continuous fermentation, we continuously put some media there, the substrate there. So that means you have to continuously add some fresh media or substrate into the fermenter, and at the same time you will take out your product, some used media from that fermenter. Okay, so you got the thing, right? You are completely adding media, fresh media, and you are continuously taking out some used media. I mean where your product is. Okay, so in this way, your fermentation will keep going on. Okay, so if you want to, if you represent it graphically, it will look like this: x-axis time, y-axis contamination. So the concentration of your substrate, that is the media, will be steady because you're continuously adding more substrate there, and also again the number of the cells will be also steady. Okay, because you're continuously taking out some cells or used media from your fermenter. Okay, Okay, so now fed batch fermentation. Okay, the fed batch fermentation is actually a modified version of batch fermentation. So what's the difference of fed batch fermentation? I mean, in comparison with the batch fermentation, in case of fed batch fermentation, you will feed the fermenter. So I mean, time to time, you will add some fresh media into the fermenter. Okay, in the fermenter, but you will never take anything out. I mean, in case of continuous fermenter, you continuously add some media there, and also concomitantly you take out some used media or cells from the fermenter. But in case of feed batch fermentation, time to time you will feed the fermenter, you will add some fresh media, but you will never take anything out from the fermenter. Okay, so in case of feed batch fermentation, the addition of substrate gives the prolonged log and stationary phase of the microbes. Okay, so like suppose if you want to produce something which is mainly produced in the stationary phase, okay, so maybe you can choose spread based fermentation, because if you want to, I mean, like for example antibiotics, okay, so most of the antibiotics are produced in the stationary phase. So if you want to have, I mean, if your target product is antibiotics, I mean, in that case, if you can, I mean, prolong your stationary phase, there is a I mean, you will get more antibiotic, right? Because microorganisms produce antibiotics mainly in the stationary phase. So anyway, if you again graphically, I mean, if you want to graphically show the fed batch fermentation, you can show this way: x-axis time, y-axis concentration. Okay, so the concentration of the substrate will be steady, because you are time to time you will put new media there. Okay, but the number of cells will increase. Okay, so the next three slide, these are actually, I mean, this the shows, this talks about some differences between the batch and continuous culture. You already, I think you already got the things. So please try to, I mean, read this out in the sketch. You will understand these things. I'll just talk, I'll try to, I mean, read a few of them. So like for example, the nutrients in case of batch, we give, we put everything in the beginning. Okay, only once, we never add anything extra. But in case of continuous culture, continuously adds nutrient there. Okay, and the termination, and in case of termination of process, okay, the batch culture is stopped after the product is formed. But in case of continuous, basically you can prolong the process, right? Because you continuously add media and in continuously take out or remove media from there. Okay, and in case of okay, these are some important points. The environmental conditions, the environmental conditions inside the batch culture are not constant actually, because in the beginning there is more substrate. Okay, no toxic substrate usually, but as the fermentation goes on, more toxic substrates accumulates there. Okay, the nutrition get depleted, so it eventually change the fermentation condition, right? Maybe the fermentation can get more acidic. Okay, the more, okay, more acidic or more salty. Okay, but in case of I mean, continuous fermentation, the environmental conditions inside the fermenter are maintained. Okay, and regarding the microbial growth, in case of batch fermentation, the microbial growth culture follows lag, log, and stationary phase. The how can I say, the most I mean, conventional growth culture thing, right? Bacterial growth culture thing. But in case of continuous culture, okay, microbial growth is maintained at optimum level, which is an exponential growth stage. Okay, so in case of continuous culture, microbes are maintained in their exponential growth phase. Okay, and turnover rate for batch culture, turnover rate is low. Okay, but in case of continuous culture, it's high. Okay, and regarding the fermenter we use, Usually, I mean, for batch fermentation, we have to use a very large fermenter. Okay, but in case of continuous fermenter, we can use a smaller fermenter. I mean, suppose, okay, so like if you want certain amount of product, okay, so like for example, you want, uh, okay, so let's think, you want 1000 kilogram of your product, okay, so if you want to produce this 1000 kilogram of product using batch fermenter, your fermenter need to be that big, right, where you can cultivate or culture enough microbes which will give you 100,000 kilogram of product, right, because we do it in a batch way. But in case of continuous fermenter, you actually don't need a that big fermenter. Okay, you need 1000 kilogram of product, but in continuous fermenter, even if you suppose think this way, if you use a 50 liter, I mean a smaller fermenter which can accumulate, I mean which can accommodate only 50 gram or only 50 kilogram, so eventually you can get 1000 kilogram from that continuous fermenter, right? Just keep it running on, okay? Keep it running on. So, okay. Okay, and then regarding the culture setup, batch culture setup is easy to make and run. Continuous culture setup is not that easy in comparison with the batch culture, because you have to, I mean, more vigorously, you have to, I mean, control all the parameters in case of continuous culture. Okay, and chances of contamination. You know, a batch culture system has very few or minimum chances to get contamination, okay, because it's kind of a closed system, okay, you have put everything there, you are not adding anything, so there is actually no chance that contamination can enter there. But in case of continuous culture, you are continuously adding new media, you are continuously taking out things, so this process is more prone to get contamination, okay. And regarding controlling methods for the batch culture are easy and quick, but controlling methods for continuous culture are complicated and time consuming. Okay, and finally, suitability. I mean, where the batch culture is suitable and where continuous culture is suitable. In case of batch culture, it is more suitable for the production of secondary metabolites such as antibiotics. Okay, and the continuous culture is more suitable for the production of primary metabolites such as amino acids and organic acids. Why? Because in continuous culture, I mean, we just saw that in continuous culture, bacteria are, I mean, the microbes, they are maintained at their exponential growth stage. And we know primary metabolites are mainly produced when the microbes are at the exponential growth phase. So if your product is a, I mean, primary metabolites, then continuous culture will be better. Okay, but if your product is a secondary metabolites such as antibiotics, in that case, we should use batch culture, or maybe we can use feed batch culture. Okay, because if you remember, in feedback culture we can design it in a way that the stationary phase will be prolonged. Okay, in that case more secondary metabolites will be produced. Okay, so that's all for uh, this part. Okay, so in the next part we'll talk more about fermentation process. Till then, be safe. Thank you.